In this lesson, we're going to define what a logarithm is and look at some of the basic attributes of a logarithm. A logarithm is the inverse of an exponential expression. Similarly to how addition and subtraction are inverses of each other, and multiplication and division are inverses of each other. Logarithms represent the exponents of an exponential expression. So if I have an exponential expression of the form b to the p equals n, so a base raised to a power equals some number argument, in logarithmic form, I would write it as the log of base b of my argument n is equal to the exponent, or the power. If you remember from our discussion of exponential functions, that the domain of an exponential function is always all real numbers, so negative infinity to positive infinity, and the range is all positive values of y, which is 0 to infinity. Now, since the logarithm function is the inverse of the exponential function, this is the graph of it. Now, realize that the base of the exponential function is always greater than 0. Because if it's a growth factor, it's going to be greater than 1. If it's a decay factor, it's between 0 and 1. So that means that my domain here has to be greater than 0, and my range is going to be all real numbers. So the domain and the range are going to flip from what it is for the exponential function due to that base being between 0 and going up to infinity. There are two special bases in logarithms, and that's a base 10 logarithm, which is called the common logarithm, and it's just denoted as log of n, so the base is assumed to be 10 in this case, and the base e logarithm. If you remember from when we were talking about continuous exponential functions, e was a special base in that case as well. Base e logarithms are called natural logarithms, and they're notated as ln of some argument or some number. On our calculator, the common log and the natural log have a special button. They're the only type of logarithms that we can calculate using these buttons. So my log key is my common log or base 10 log. My natural log is my base e logarithm. Let's practice writing from one format into another. So we're going to start with an exponential expression and rewrite it as a logarithm. So 3 squared is equal to 9. As a logarithm would be written log base 3 of 9 is equal to 2. Remember that logarithms are always equal to the exponent of an exponential expression. That's what they represent. So 7 to the negative 1 is 1 over 7. As a logarithm would be log base 7 of 1/7 is equal to negative 1. 10 cubed equals to 1,000 would be log of 1,000 is equal to 3. Again, notice how I didn't write the 10 as the base since it's understood that this is a base 10 logarithm. And lastly, we have e to the 0 equals 1. So we have the natural log of 1 is equal to 0. Let's now go in the other direction, so taking a logarithm and rewriting it as an exponential expression. So I have log of 1 over 1,000 is equal to negative 3. So that is a base 10 logarithm, so 10 to the negative 3 is equal to 1 over 1,000. What's nice about going from logarithm to exponential form is that it's easy to check if your answer makes sense. 10 to the negative 3, we know that negative would mean that the 1,000's in the denominator of the fraction. So that answer makes sense. Log base 5 of 625 equals 4, so 5 to the 4th is 625. The natural log of e to the 5 is equal to 5. That's pretty easy. E to the 5th is equal to e to the 5th. Definitely makes sense. And lastly, log base 7 of 7 is equal to 1. So 7 to the 1st power is equal to 7. Again, that expression makes sense. Let's evaluate logarithms using our calculator. So here it's pretty easy. We're using our logarithm keys. So I have the log of 786. So I have my log key, 786, and hit enter.
Okay, and I'm going to round it to 4 decimal places, so it's 2.8954. The bottom one, I have the natural log of 654. So that's 6.4831. Okay, now we're going to solve the following exponential equation by estimating the solution, solving it graphically, and then using a logarithm. So I want to solve 10 to the x is equal to 150. So when we think about powers of 10, we think of 10, 100, 1,000, 10,000, and so on. So I don't really know what my exponent should be for 10 if I want it to be equal to 150. So let's think about estimating the solution. So here are my powers of 10 that I just said. 10 to the first is 10, 10 to the second is 100, 10 to the third is 1,000. So I know, since I'm looking for 10 to the x equals 150, that my exponent has to be somewhere in between 2 and 3 right here. So we can say that x is between 2 and 3, but it's going to be closer to 2 since my output value here is 150. We can then use this result to help us solve this graphically. So my window is pretty easy if I think about my powers of 10. I know my exponent, my x value, is going to be between 2 and 3. So I made my x min 2, my x max 3, and I'm counting it by ones. My output values, I'm just going to match up with the input values. So I'm making my minimum 100, my maximum 1,000, and then I'm just going to count them by hundreds so I get a nice graph. So into y1, I put 10 to the x. Into y2, I put 150. I typed in our window that we discussed. I hit the graph key and then found the intersection. So remember, that was going to second and then that trace key, option number 5. So we found that our x value is approximately 2.1761. And again, this makes sense with what we had talked about when we were estimating the solution. We said that x would be between 2 and 3, but it would be closer to 2. Lastly, we want to solve this by using a logarithm. So since it's a base 10 exponential function, we're going to have a base 10 logarithm. Since we have a base 10 logarithm, we could actually use our calculator to do this. So the log of 150 is equal to my exponent x. I just typed in log of 150 into my calculator and got my output. What's nice about having that estimation and graphical method is when I have something that I cannot just type right into my calculator. So say I have something like 5 to the x is equal to 27. Okay, that's not something, I don't have a base 5 button on my calculator. So being able to estimate where that solution would be and then find it graphically is very helpful before learning how to solve these exponential equations using algebra. So just a little review of what we've talked about today. We have logarithmic expressions, which are inverses of exponential expressions. My exponential expression is b to the p power, so my base to a power, and that's going to be equal to some number, some argument. My logarithmic expression is always going to be equal to that exponent. So the log will have the same base, and we're taking it of that argument or of that number. There are two special bases that we have, base 10, which are common logarithms, and base e, which are natural logarithms. We can calculate base 10 and base e logarithms using our calculator, but those are the only ones that we can actually use our calculator for. And lastly, we can find the values of exponential expressions that are not nice, easy numbers like 3 to the x equals 9 by using an estimation approach and using a graphical approach.